Hi, Daisy. I have a question for you. I've collected different data views on a set of patients, including gene expression, DNA mutations, and proteomics. I'm trying to predict their response to treatment. How can I do that?
Here is your setup. You could concatenate the views into one big feature matrix and then apply supervised learning. This is called early fusion. Or you could fit separate models to each view and then combine the predictions at the end, which is known as late fusion.
But which approach should I use?
You can use a new method called cooperative learning. It fits a continuum of models spanning both early and late fusion. It has a hyperparameter that determines where we are along the early-late spectrum. Here is how it works. Let's suppose we use linear models for our supervised learners. Then if y is our target and x and z our feature views, we can express early fusion as minimizing the objective 1 over 2 times the sum of y minus x beta minus z theta squared over all choices of weights beta and theta. To get late fusion and everything in between early and late fusion, we add an agreement penalty, rho over 2 times the sum of x beta minus z theta squared.
What's the idea behind this?
We imagine that there are hidden underlying factors that are correlated with both of the feature views and the response. The agreement penalty exploits this underlying structure by encouraging the predictions from different views to align. Rho has two special values. When rho equals 0, this gives early fusion. And it turns out that when rho equals 1, this gives a form of late fusion exactly.
Very cool.
Trying different values of rho gives an entire family of solutions that encompass both early and late fusion.
But how do I pick that hyperparameter rho?
It will do it for you using cross-validation. The data will tell you what kind of fusion works best.
How can I determine which features are important?
Cooperative learning uses the lasso for its fitting, so that you get a sparse feature model. It tells you which features are the most predictive. Let me walk you through an example. Assume that we have collected transcriptomics and proteomics data for a set of patients, and we want to predict the response to treatment. We split the data into training and test sets. We fit the model using the training set, select the hyperparameters using cross-validation, and evaluate the performance on the test set. Here is the output. The CV error is the lowest when the weight of the agreement penalty rho is 0.5. With this selected value of rho, cooperative learning achieves the lowest test set mean square error as compared to early and late fusion. We also get the contribution of each view in making the prediction as benchmarked by the null model.
Well, Daisy, that all sounds great. Can I have this done by tomorrow?